Hello everyone, welcome back. I hope you enjoyed that little embryo activity. Pretty hard to figure out if one was human or not. Pick out your own family relative. Um, and I also hope you enjoyed the video. So today we're going to continue our discussion on evidence of evolution. We could never totally exhaust looking at the evidence for evolution. I mean, there's literally hundreds of thousands of pieces of evidence for evolution. But we'll just highlight a few. And again, remember, you're going to become an expert on a few of these pieces so that you can discuss it in your first test. So as you little review, the theory of evolution states, I hope you know by now, that all life on Earth descended from a single common ancestor, and a corollary, that life originated in simple form and became more complex and diverse over time. So right now, we've been looking mainly at the fossil record from the last lecture. So I want you to think to yourself, did the fossil record really do more to illustrate this first statement or the second statement? I would argue that it does more to support the second statement, because when you look at the fossil layers, right, for well over 1 billion years, we could see only single-celled life forms that were prokaryotic, and then after life had existed for almost 2 billion years, well over 1.5 billion, then we started seeing cells with a nucleus. And finally, life had existed for 2.5 billion years before we found multicellular organisms about 1 billion years ago. So again, if you think of the fossil record slicing up layers on the tree of life, you can easily see by looking at the patterns of fossils, because remember, these are only snapshots of this time or this time. By looking at the patterns of fossils, I think overall the fossil record supports that second statement there. Now here is a statement from a biology text that I no longer use. Evolution proceeds by modifications of organisms which already exist. Now I want to do a little mini thought experiment with you. I want you to think of the evolution of human transportation. So how did humans originally get around? What was the only way we got around? Well, by our bare feet, right? Then we started wrapping our feet, some kind of animal skin, sort of, really primitive shoes, then sandals. Then we started riding animals, right? Camels, horses, um, elephants. And then a huge, huge, huge innovation was that of the wheel, right? So then we had chariots and stagecoaches. And another quantum leap, if you will, we had the automobile, thanks to Henry Ford, and then thanks to the Wright brothers, airplanes, then jet planes, and space shuttles. Now, when NASA goes to build a space shuttle, do they have to start with a sandal and work their way up? No. I mean, when you take a tour of the space shuttle, you don't say, oh, look, there's a stick shift from a Model T Ford, do you? No, because NASA can build a space shuttle from scratch. But if evolution is true, that all life came from a single common ancestor, the only way to get a new type of organism is to modify an existing type of organism. And we would expect to see evidence of that if we examine living things today. So, the first line of evidence that you saw in the movie is called homologous structures. Again, homo means alike. So, definition of homologous structures. How are they alike? They're similar in shape and in pattern of arrangement in the body, but they have different functions in different organisms. So to repeat, they have similar shape, similar patterns of arrangement, and even as it turns out, similar, really the same embryological origins, but they typically have different functions in different animals. And the example you saw of that in the video were bones. And the question is, can you give detailed descriptions of homologous bones? Because I'd expect you to do this on your test. But you just saw a diagram, something like this in the movie. And I don't think you can give really detailed descriptions, all right? So what you're seeing here in the foreleg of all these different animals, horse, humans, I can't even read that anymore, crocodile, all right? You see a humerus connected to a radius and an ulna. A humerus and a radius and ulna. But to me, this would not convince me that this is evidence of evolution, because it's like, okay, you just colored them the same way. Well, when we meet in person, you will see how the humerus of a human and the humerus of a monkey and a humerus of a cat, how they're not just similar, they're identical almost, except in terms of scale. Every little nook, every little cranny, every little ridge, and this is something you just really have to see for yourself in person. So again, but we can do this much. If you think about it, if you look at the human forearm and you look at the arm of a monkey and the flipper of a whale, maybe this is a whale, and the wing of a bird, do they look at all alike from the outside? Human arm, flipper, wing, monkey arm? Not really. And do they have the same functions? Absolutely not. We use our arms to grab things with. The monkey has to brachiate, swing from branch to branch. The whale uses it to swim, the bird to fly. So if you saw these limbs from the outside, which you have, and you know they look totally different from the outside and have totally different functions, would you necessarily predict they would have the same bones inside? I mean, would you have been surprised if the internal structures were totally different? Probably not. Yet, in all these vertebrate forearms, we do see the exact same bones, the exact same shapes, and the exact same patterns. All right. So what causes an organism to have the same bones? Well, what causes any of your traits? It's you have the same genes. All right, so if you have the same traits, you have the same genes. Well, where did you get your genes from? Well, you got them from your parents. And where did they get their genes from? Well, they got it from their parents. Well, if a horse and a human and a crocodile and a whale all have a humerus, then they must all have the genes for a humerus. That's this bone right here, which you will see in person. And if they all have the same genes, that would imply that if you go far enough in time, they share a common ancestor. Okay, so this is the type of argument you're going to have to make in your essay. You're going to have to describe some evidence in detail and give the explanation for it. Ready to try it on your own? There's just showing you, these are our fingers. They're called phalange, these finger bones. And these are the bat phalanges, adapted for their wing structure. All right, what you did get to look at is some nice pictures of embryos. Now, all animal embryos go through these stages. Cleavage, now, you may or may not have heard that in Bio 151. I know I teach my students, but maybe not everybody does. Cleavage is basically just rapid mitosis without cell growth at the beginning of embryonic development. So if you know what these words mean, great. If not, you're going to learn them later in this course when we talk about animal development. But anyway, if you don't know what they mean, don't worry about it. You won't have to know them for test 1. But all animals undergo through cleavage stage, morula, blastula, and the gastrula stage. But all vertebrates, all animals having a backbone, all animals whose skeletons are basically bony, what did you observe? Well, here is a little alligator embryo, and here is a little mouse embryo. And you probably would not identify this as an alligator or a mouse if I didn't have it labeled. And I think they look pretty much like the pictures you looked at. So hopefully you observed some things like all the embryos had an eye that was really, really large relative to its head size. Now, when I do this exercise in class, students will say, oh, their eyes were really big. Well, consider this whole embryo here is maybe only a centimeter big. I would argue this eye is actually quite small. But compared to the size of the head, oh my goodness, it's humongous. So all these embryos had proportionally large eyes, and again, their head was proportionally large compared to their body. All right, so these heads were all they were all large and lumpy, whether it was going to end up to be a crocodile or a mouse or a chicken or a human or whatever. All the vertebrate embryos had tails, even if it was going to be human. All the embryos you might have observed were in this C shape. Some people call it crescent shaped. And all these little embryos had these little limb buds. All right, no matter whether this limb bud was going to end up to be a wing or a hand or a leg, all right, all these little embryos had limb buds. So and these were different than some of the embryos you looked at. So you might even make another hypothesis, like if you looked at an elephant embryo, it would probably have the same features too. So what is the best explanation? I mean immediate explanation. Well, if embryos have the same traits, like curled up shape and curled up tail, all right, then they must have the same genes. So if an alligator embryo and a mouse embryo have the same traits, then you would have to argue they must have the same coding, the same genes. Because we could take limb buds as an example. The reason why they both have limb buds, they both have the genes for limb buds, as well as these other traits. And they got these genes from their parents, who got it from their parents. So the logical conclusion is, if you go far enough back in time, an alligator and a mouse share a common ancestor. Now, can you look at two embryos and say, "Whoa, evolution is true. All life comes from a single common ancestor"? I don't think so. All this is right here is evidence that the alligator and the mouse have a common ancestor. What you have to remember is evolution is called a theory, and there are, again, hundreds of thousands of data points that support this theory. So when you write your essays, you can't say, "Oh, well, this shows that all life comes from a single common ancestor." No. If we compare the traits of an alligator embryo and a mouse embryo, this is evidence that an alligator and a mouse share a common ancestor. But again, if you compare these embryos to a chick embryo and they have the same traits, well, that's the evidence that the mouse, the alligator, and the chick have a common ancestor. And you throw in the human, that too. So you get the picture. That this is, since, again, all tetrapods actually develop limb buds in the same way. That's animals with, these are vertebrate animals that develop 4 limbs. This is strong evidence that all tetrapods, all vertebrate animals, share a common ancestor. And I think I just answered that question, so hopefully you took notes on it. All right, vestigial structures I think are really cool. Hopefully you picked up those in the video you watched. The definition, vestigial structures are structures that have no function in the organism that they're found in, but are presumed to have been functional in an ancestor of that organism. So I'll repeat. A vestigial structure has no function in the organism that it's found in, but is presumed to have been functional in an ancestor of that organism. So in other words, we can think of vestigial structures as evolutionary leftovers. So what were some examples you saw in that movie? Do you remember in the video you watched examples of vestigial structures? Are you thinking the eyes on a blind cavefish? Again, those fish were blind. It's not just that they lived in the dark and so they couldn't see because it was dark. The eyes actually did not work. So why would an animal spend energy, precious energy and resources developing eyes that don't work? Right? What's the best logical explanation for this? Well, we know if they have eyes, then they must have, yes, the coding, the genes for the eyes. Where did it get the gene for the coding from the eyes? From its ancestors. So the most logical explanation is that these fish descended from other fish that could see. They got their genes for eyes because their ancestors had genes for eyes because their ancestors needed eyes to see. Another example is the human coccyx, our tailbone. Why should we have a tailbone if we never develop an external tail since birth? Well, once again, we have genes to form a tailbone, which we got from our ancestors. So we assume that our ancestors had genes to form a tail because, yep, somewhere back in the family tree, your ancestors had a tail. Another example you might have noticed from the video were those little nubby nubs on the side of pythons and whales. Well, those are actually vestigial femurs. Your femur is the biggest bone in your body. That is your thigh bone, your upper leg bone. Now, why would pythons have a little leg bone if they don't have little legs? Again, we know if they have a little leg bone, they have genes for that leg bone. Where did they get the genes from the leg bone? From their ancestors. Well, why would their ancestors have gene for leg bones? I guess you would assume then their ancestors had legs. So yes, that's current evolutionary theory that snakes descended from their ancestor reptiles had legs, from legged reptiles. So again, this is the language we need to use in explaining why this is evidence. You know, it's just not good enough to say, oh, these embryos look alike. You have to be able to explain to me on a test how they look alike. In other words, you need to explain someone who knows nothing about evolution how this supporting evidence works, just like we're doing with the vestigial structures. I don't know if you're familiar with a little kiwi bird. It lives in the Australia, New Zealand area, and it has teeny, teeny, tiny little wings. And now let's talk about how we know if a structure is truly vestigial. Basically, the test is if you could amputate that structure and that animal is not at a survival or mating disadvantage. So these wings are really tiny, they're a flightless bird, and if you amputated them, that bird would not be at a survival disadvantage or a mating disadvantage. So you can apply this test to others. So people have asked me, well, is the human appendix vestigial? And most scientists I know would argue, yes, you can have your appendix removed and you are not at a survival disadvantage or a mating disadvantage. So let me ask you about a couple of other examples. What about a wings on an ostrich? Because that's another flightless bird. Would you argue vestigial or not vestigial? I'm trying to find my pointer options here. So while I'm doing that, you can think about that. The ostrich. Is the ostrich, oh, I'm just having all sorts of trouble. Are the wings on an ostrich vestigial or not vestigial? Well, let's apply the test. If you could amputate the wings of an ostrich, would it be at a survival or mating disadvantage? All right, do you remember when we saw that movie? Oh, I'm having all sorts of interruptions today. I don't know if you can hear my phone ringing. If the wings of an ostrich were amputated, it would have trouble running because it uses those wings for balance. Also, in the video we saw, birds have very intricate mating. They have very